In this video, we demonstrate vrAIn, an orchestration engine powered by deep learning to optimize jointly the allocation of computing and radio resources in virtualized radio access networks. vrAIn monitors the buffer states and the available channel quality information over time across all users and all radio access points, or RAPs, in the system, which we refer to as contextual snapshots. These contextual snapshots are fed periodically along different decision periods into vrAIn's main engine for processing. We will describe more in detail this engine or resource manager later. As a result, we map a given contextual snapshot into a pair of policies. One, a CPU control policy, which imposes an upper bound on the relative time that the computing platform can process each virtualized access point. And two, a radio control policy, which establishes an upper bound on the modulation and coding scheme eligible by each of the virtualized radio stacks. In addition to contextual data, monitoring probes on the radio stack measure a number of network key performance indicators, which we use to train the internal models of vrAIn's engine. We first demonstrate a use case where the goal is to minimize the use of computing resources when the computing capacity of the system is unlimited or over-dimensioned. To this end, we deploy one virtual radio stack and observe how vrAIn adapts the allocation of CPU resources to the dynamics of the contexts without any restriction on the availability of computing capacity. This is the dashboard we have implemented to control the different parameters and use cases of our demonstrator, where we can select between one or two virtualized radio stacks. For this use case, we bootstrap the system with one virtualized radio access point. Let's explore the trade-off between performance and usage of computing resources. To this end, we let the wireless link enjoy good conditions and select a high Q value to favor performance over CPU savings. We can observe that vrAIn assigns substantial computing resources to guarantee good throughput. If, instead, we reduce the Q parameter, which is intended to favor CPU savings over performance, we can observe how vrAIn assigns considerably less computing resources to the virtualized stack. Importantly, in order to accommodate such low CPU consumption, vrAIn calculates a radio policy that imposes rather low modulation and coding schemes, and hence lower throughput. If the radio stack used high modulations in this context, even with high channel quality, the CPU consumption during peak loads would exceed the allocation of computing resources, yielding substantial decoding errors. This is precisely what happens with legacy compute-unaware radio schedulers. To show this, we select state-of-the-art mechanisms in our dashboard. We can observe now how the radio stack selects modulations over the policy imposed by vrAIn, matching the good channel conditions experienced, but unaware of the unavailability of computing capacity. As a result, the bit error rate grows, leading to zero throughput. For the second use case, our goal is to assess the performance of the vRAN system when its computing capacity is under-dimensioned. To this end, we deploy two virtual radio stacks over a single CPU core. In this context, the aggregate computational demand when the load of both virtual radio stacks peak at the same time is well above the system's capacity. Observe how, given that the contexts of both radio stacks evolve in an identical manner, vrAIn shares equally the computing capacity among the radio stacks. However, 50% of computing resources is not enough to serve highly modulated traffic when the demand is high. To solve this issue, when the peak load is high for both radio stacks, vrAIn assigns low radio control policies to guarantee that the computational needs of both radio stacks respect the limited resource allocation. Importantly, vrAIn optimizes the control policies to maximize throughput while guaranteeing near-zero bit error rate, as evidenced by this plot. vrAIn can also assign priorities. We select a high Q parameter on radio stack 1 and a low Q parameter on radio stack 2. With this, we are requesting vrAIn to favor performance on radio stack 1 over that of radio stack 2. Observe that, to satisfy our request, vrAIn shifts computing resources from radio stack 2 to radio stack 1, around 10%. This allows vrAIn to assign high radio control policies to radio stack 1 at the expense of the radio policies imposed to radio stack 2. As a result, radio stack 1 can attain higher throughput than earlier at the expense of lower radio policies and hence low throughput in radio stack 1. The technical details of vrAIn and the dataset we have used for training can be found in the links that you can see on the screen. Thanks for watching.